Good morning, everyone. We will start today's session momentarily. Thank you.
Okay.
Okay. Good morning, everyone. Can you all hear me? Okay. Great.
Yes.
All right. Welcome to our discussion today. So this is our second session for the technical exchange between UDC and the NASA Johnson Space Center. So my name is Jiajun Xu. I'm the associate professor here of Mechanical Engineering Department, and also I'm the director for this NASA-funded Center for Advanced Manufacturing in Space Technology and Applied Research. So today, we're honored to have subject matter experts from NASA Johnson joining us, and also my colleagues here to have this discussion on how we can collaborate and to on areas related to in situ resources utilization. And before we start today's session, I just want to give a huge shout out to folks at Johnson, Mr. Black Scott and Brandon, for helping us and coordinating this event, making this possible. We had a session last month, and this is our second session, focusing on a few areas. So thank you for helping making this possible. And since we have about 1.5 hours today for this discussion, so I think we can divide it into 3 sessions. So we can have our NASA experts present at the beginning for about half an hour, and then we have some faculty from UDC who will be presenting their research. And then I know we have a couple of students joining us today as well. So if time allows, we can also have them present. And then we will save some time at the end for some discussions. But I think we can, just feel free to ask any questions during the presentation. I think if you see anything that you would like to ask, and please feel free. So for this session, so here is the list of the people who will be presenting today. So as I mentioned earlier, we have Mr. Jerry Sanders from NASA Johnson Space Center joining us today, and Mr. Black, Scott, and Brandon will be from the OSTEM office who help coordinate this event. And from UDC side, we have Dr. Lei Wang, Azam Hossein from UDC, Civil Engineering Department, will be presenting today. And we also have Dr. Chiu Shi Chen and from Clemson and his team who are collaborating with us on this project will also be presenting their research. And we have a couple of students also here. So I hope I didn't miss anybody. There may be a couple other colleagues will be joining us as well along the discussion. So without further ado, I would like to request our Mr. Sanders to, if you have any slides you want to share, I will stop sharing my screen so you can start sharing your presentation, and then we will go from there. And I will be moderating today's session, so any questions, feel free to type into the chat or let me know. Yeah, so thank you, and let me stop sharing my screen.
Okay.
Let's see here. Okay, I think I already stopped. So yeah.
Can you see my screen now?
Yes, I can.
Okay, I'm going to turn it into slideshow mode. So thank you very much for allowing me to talk to you all this morning. I'm going to talk about in situ resource utilization going on at NASA. And so I'm going to start with the lunar architecture, a little bit of that discussion, talk a little bit about lunar resources in this first section, and talk a little bit about the purpose and challenges of ISRU. And then in the next section, I'll talk about the development strategy. So I'm not sure what background you have, but NASA is working on what's called the Artemis program. It's humanity's next step, giant leap into space. The premise is to return to the moon and go on to Mars with the first woman and first person of color, hopefully by 2024, but that may slightly be delayed. To do this, we will also want to learn to live and work on the moon and translate those experiences into capabilities that the United States and the international community can use to explore Mars. And at the same time, use these activities to inspire the next generation of explorers, researchers, scientists, and such as yourselves. A major effort or guidance as part of this is the Space Policy Directive 1, which came out from the last administration, which basically says that the United States will lead this program, but will do so with both commercial and international partners. So the beginning of the Artemis program is to basically develop the capability to send humans back to the moon again. And so there's a series of missions, Artemis 1, which will hopefully happen, let's see, towards the end of this year or early next year will be the first launch of the Space Launch System with the Orion spacecraft. This will be uncrewed. The next mission after that, Artemis 2, will have the first crew on board. At the same time, we're looking at setting up what's called the Gateway in a high orbit around the moon, and Artemis 3 will be basically another mission going to this gateway, potentially spending more time in space, with Artemis 4 being the first mission to the lunar surface with crew. After that, we look at increasing both the capabilities of the gateway as well as capabilities on the lunar surface for extended duration and sustained exploration activities. So, we have the crew landing system, we have pressurized rovers, surface habitats, but we also start looking at advanced technologies such as fission nuclear reactors and ISRU plants for making mission consumables and propellants. An important part of this activity is the Artemis Accords. And I don't know if you get into space law itself, but basically the use of lunar resources or space resources in general is a little bit ambiguous in the Outer Space Treaty. So NASA and several other countries have written laws, but in particular, NASA is bringing forward the Artemis Accords, which has 8 guiding principles and best practices for how to explore space. One of those is the use of space resources. So they're discussing how we can smartly use space resources and still stay within the Outer Space Treaty. When you look at the moon, we consider 2 major resources. One is the lunar regolith itself. So you look up at the moon and you see dark patches and lighter patches. The dark patches are Mare basalt, very interesting mixture of volcanic materials, including a mineral called ilmenite, which is an iron oxide, titanium oxide mineral. The lighter gray material is highland. It's mostly a north acidic in nature. And then there's some other aspects, subgroups like pyroclastic glasses and creep, which includes rare earth elements. The interesting thing is when you look at the minerals, over 40% of the mass of the minerals is oxygen, something between 40 and 45%. So just trying to get that oxygen out is a very large interest within NASA, as well as some of the metals like iron, aluminum, and titanium. Besides that, though, over the years, we've learned more and more about what might be in the permanently shadowed craters in the North and the South Poles, including water. We only have one real ground truth, and that was the L-Cross impact in 2009. And some of the constituents of the plume that was imaged after the L-Cross impact is shown on the bottom right. And basically, it looks like there may be something on the order of 5.5 weight percent water, but that's plus or minus almost 3 weight percent. So it could be very little, could be a lot. And how deep that is, how distributed it is still a big unknown. Looking a little bit more at the rocks that occur, or the minerals, we can see, for example, I mentioned anorthosite. It's either calcium or magnesium silicates. You get a lot of silica and aluminum and calcium from that. Ilmenite is found more in the mare, in the equatorial regions, and here you can get significant amounts of iron and titanium as well. And it starts showing some of the things that you might do with those constituents downstream. One of the important things to recognize is, unlike the Apollo missions, which primarily occurred in the equatorial region, the Artemis program's looking at in particular the South Pole, looking at areas where you have significant amounts of light, these peaks of eternal light, as well as the permanently shadowed craters where we may have significant amounts of water and other interesting volatiles. And so a lot of work is going on in terms of using different types of measurements, thermal, sunlight, minerals, and volatile types of orbital measurements to identify some potential areas where you have lots of light next to permanently shadowed craters, next to what may be water resources. So why do we want to use resources in space? And so we kind of broke it down into 4 major categories. One is, if you use resources in space, you can reduce your mission mass, as well as your overall architectural mass and cost. And the biggest thing on the next chart I'll mention is what's called the gear ratio. And so for every kilogram of anything you land on the lunar or Mars surface, you have to work yourself backwards and say, well, how much propellant did I need to use, and what's the spacecraft dry mass and stage mass and things like that. And it turns out that it's somewhere between 7.5 and a little over 11 kilograms in general. For every kilogram that you land on the lunar surface, you have to launch into orbit. And so if I need, say, from Mars, you need about 30 metric tons of propellant to get the crew off the Mars surface back into orbit. You multiply that by 10, say, and that's 300 metric tons of payload that would have to have been launched into orbit just to provide that propellant. So you can get significant mass savings along those lines. You now start thinking about reusability of assets too. You have your gas station there, so now I can fill up and reuse my landers or stages. The other thing is crew safety and mission assurance. When you start having the ability to make things to whether it's consumables or radiation shielding or spare parts, you start changing the dynamics of the mission and how you can protect the crew and ensure the mission is successful. You also can start dealing with things that might not have been possible without using ISRU, extending missions beyond what you bring from Earth, increasing your surface mobility in science. And then lastly, there's a lot of things that we do with respect to ISRU, mining, processing, and such that can be used on Earth to help us with some of the challenges that we have here in terms of reusable energy and CO2 reduction and repurposing and water cleanup and such. So this is what I mentioned about the gear ratio. And so working backwards, you basically see a lot of different propellant stages and things that you need to do. And we've done calculations for both the moon and Mars over the years, and you can have significant savings. 300 metric tons is approximately 3 launch vehicles at $1 billion per piece. That's, $3 billion worth of savings right there. So when we think about ISRU, we kind of have a whole, you have to consider the whole ecostructure. We say prospecting to product. So in the top left, we look at prospecting on the moon. We're looking at water. On Mars, we look at what hydrated minerals and subsurface ice as you go away from the poles. As I mentioned, we look at excavating and extracting the oxygen from the lunar regolith, which is kind of similar to extracting water from hydrated minerals. We also look at the polar ice in the permanently shattered craters, and that feeds us to a lot of potential customers, landers, rovers, habitats, crews, as well as supporting civil engineering and surface construction activities. So for NASA, we have 3 major reasons for why we're moving forward. One is obviously to help sustain and grow lunar surface exploration, understand the resources, develop capabilities for mission consumables and propellants, and basically learn how to live off the land. We're going to take those technologies as well as our operations and practice what we would do on Mars. The moon is nice in the fact that we're only a few light seconds away from a communication perspective. With Mars, obviously, we're much different. Depending on the orbits and where the Earth and Mars are, a single transmission can go anywhere, I think, from 8 to 40 minutes. So round trip discussions and operations become much more difficult. You could joystick a excavator on the moon. You can't do that for Mars. So you now have to have much more autonomy associated with what you want to do on the Mars surface. So we can use the moon as a practice ground. And then the last thing is really, how do we expand our economy, both on Earth as well as in space? And so the things that we try to do is to bring along commercial partners and spin-ins and spin-offs for what we can do to help situations on Earth. And so we have several challenges that we need to deal with. First of all, understanding the resources. We still don't know a lot about what's in the permanently shattered crater besides the L-cross impact. And when we talk about Mars, we have to consider planetary protection rules. We don't want to contaminate Mars, and we don't want to bring anything back from Mars that obviously could be harmful to us. So there are things that we have to deal with in terms of sterilization and where we can go. And there are technical challenges. We have to operate for long periods of time. And we have to do this. We try to be as economically feasible in terms of the processes, how much hardware you need, and how much energy you need to do these things. We have operational challenges. We're operating in extreme environments. We can have extreme vacuums, extreme temperature ranges. We have the dust and the radiation and the abrasiveness of lunar regolith. We also have a lower gravity, which changes how we will operate and do things. We have this long duration activities where we may not have crew. The early Artemis missions are for a few days, maybe up to 30 days, whereas our hardware needs to operate continuously. And then we have integration challenges. How do we make sure that the products that we are making are useful to other customers? How do we insert and make sure that the architecture takes the best advantages of what we're doing? So that's the why we would want to do ISRU and where we might fit in. Now I'll start talking a little bit more about the how are we doing this. So within NASA, we have different mission directorates. The human and operational directorate, exploration operations directorate, or HEOMD, is in charge of human exploration. We have our science mission directorate, which is in charge of science missions. NASA has a mission directorate specific to space technology development. And within this mission directorate, we've divided basically our work into four major thrusts. What does it take to go to the location you want to? What does it take to land there? What does it take to live and work there? And what does it take to explore in these extreme and interesting environments? And ISRU falls into the live category, and one of our major outcomes is to develop scalable production capabilities to make sustainable commodities for both the Moon and Mars surfaces. And to do this, basically, the Science Mission Directorate has guiding principles that it will try to develop critical technologies for sustainable lunar presence and for future missions to Mars, as well as science that both the HEOMD Human Exploration Group and the Science Mission Directorate can use. And we do this through funding critical technologies across the technology pipeline and working with industry and academia. So this is what I call the snake chart, but it's the technology pipeline. And it talks about everything from working at the extremely low technology readiness level through our NIAC programs. We have grants and early career activities, early faculty initiatives and such. The mid technologies through our SBIR Small Business Innovation Program, all the way to partnerships and prizes that we do with industry, academia and such. And finally, technology demonstrations at the high technology readiness level. To also help with exploration, NASA set up what's called the Lunar Surface Innovation Initiative within STMD, and it has 6 major areas, 2 of which are very closely linked: my area of in situ resource utilization, as well as our surface excavation and construction. We've also set up a consortium with the Applied Physics Lab called the Lunar Surface Innovation Consortium, and its purpose is to also help reach out to industry and academia and build a community of practice, and to help engage NASA with these outside organizations, so that it's not just NASA leading and running things, but that basically everybody has a shared interest and shared values and can all participate. So to do our development, we plan on doing a lot of ground and flight development. We have what's called CLPS, which is the Commercial Lunar Payload Services. These are smaller landers that can send robotic precursors to the Moon. Early missions may be on the order of, say, 30 to 100 kilograms, but over time, larger missions in the several hundred kilogram payload class will fly. We'll look at developing and flying critical technologies to understand the resources and different processes, how you might excavate, how you might extract oxygen or mine water, and then work on what we call a pilot plant, which is an end-to-end demonstration of all the capabilities we need before we would set up a full-scale system. And so this kind of is a pictorial where, you know, we work on our resource characterization and prospecting. We have the 2 paths for water mining or oxygen extraction. And then we basically have to make sure that the consumables, the water, the oxygen, the methane or fuels that come out go to the different customers. as well as the plastics and the regolith and the metals go to our construction and manufacturing folks. And we take in things as well. We can take trash and waste from our habitats and crew and use that as a resource for processing and making things. We've tried to look at the near term to long term. Where do we want to be? Where do we want to go? And so on the extreme right hand side are some studies that were performed that if we were to use lunar propellants to support going to Mars, or if we set up a very large commercial cislunar space activity, we're talking hundreds to thousands of metric tons of propellants per year. We're way on the left-hand side at the moment. We're looking at demonstrations in the tens of kilograms. Our pilot plant probably is in the high hundreds or low thousands of kilograms of product per year, and our initial production plant is probably in the 10 to 30 metric tons of product per year. That would support probably one crewed mission, one ascent mission per year, depending on the size of the crew and the spacecraft. And so we're following the two pathways. The water resources, what does it take to do that, as well as the oxygen resources and how do we extract those. And so for both of those pathways, we have questions that we need to ask ourselves and answer. For water, is there sufficient quantities of water there? Can we extract them efficiently? For oxygen extraction, can we excavate the harsh, abrasive granular material? Can we separate it out into different minerals if we need to? Can we extract the oxygen, and how pure is that product? And based on answers to these questions through ground development and robotic precursors, we'll decide which pathway will fly towards the pilot plant. So some of the things that we're looking at in terms of the resource assessment or prospecting, there's two phases. The exploratory phase, which is I just want to go in and take a quick look. We could do that by flying over permanently shadowed craters, sending small rovers into permanently shadowed craters, landing in permanently shadowed craters, or even projecting items from outside the crater into the crater. These are all things that we've looked at and are considering. Now, at some point, we need to do serious prospecting, understand the full extent of the resources. So this was going to require some kind of a mobile asset that could spend a significant amount of time in a permanently shadowed crater, performing some kind of a scanning, driving approach, and looking for what we'll call hotspots where high concentrations are. And this image at the top right is actually of a field test we performed in Hawaii in 2012, where we used different instruments to try to locate where we had some simulated ice locations and such. We're also looking at different mining operations and what that might entail and where we might go. So like, for example, one possible location is near Shackleton Crater. There's a much smaller one here that's a couple of kilometers, four-ish kilometers in diameter. There's areas of high light concentration nearby that we might be able to operate and mine in here and send out the water initially for processing in the sunlight. But we have to take into a lot of considerations, how we might remove the water from the permanently shadowed crater, how we might mine the water. But a big aspect is, how do we get power into the permanently shadowed craters? Do we have a long cable? Do we beam the power in from the outside? Do we have a nuclear reactor inside the permanently shadowed crater? These are all things that we're examining. For oxygen extraction from regolith, this is something that we've looked at quite a lot over the years during the Constellation program. well, in the past, there's something on the order of 20 to 30 different methods have been proposed. From 2005 to 2010, we looked at 3 in particular: hydrogen reduction, carbothermal reduction, and molten regolith electrolysis. We are re-examining those, as well as others such as ionic liquids, and vapor phase pyrolysis is another area that we're considering. Each of these require typically a significant amount of energy or some kind of a strong acid or base to break up the minerals. And at the same time, we have to understand the whole mining operations, how you control your rovers, and where you control your excavation sites and your dump sites, and all of this has to be done autonomously. So you have to have navigation aids and communication and power. So we're looking at basically the whole infrastructure as to what would be needed. The interesting thing is we started already. So we have the Lunar Reconnaissance Orbiter in around the moon right now. It's been there since 2009. We have a number of missions that are planned to go to the moon. Several CubeSats on the Artemis 1 mission are specifically aimed at looking at what might be in the permanently shadowed craters through different instruments. We have a camera on a Korean Pathfinder lunar orbiter that can look into permanently shadowed craters. And then we have some surface missions that are starting to look at, in particular, you may have heard of Viper. This is a rover that will fly in December of 2023. It has a drill and several instruments to bring material up from the subsurface down to about a meter. It will operate for several months and drives tens of kilometers. As a precursor to that mission, to make sure that the drill and the mass spectrometer work, we have what's called Prime 1, which will fly a year in advance. And then from a bigger picture point of view, this kind of gives you an idea that, we're on the left-hand side, we're working on ground development activities. Prime 1 and Viper will happen early in the next few years. We're looking at some scalable demonstrations, and hopefully by the end of the decade, we'll be ready to fly a pilot plant. And I'm not going to go through these charts. I'll send them to you to look at afterwards. But for each of these different areas, we have a significant amount of ongoing development activities. So in the area of resource assessment, we have internal and external projects going on for different types of instruments. We have several missions already selected for CLIPS that will be flying a bunch of these instruments that we can use for prospecting. We are looking at different mining techniques for how we would extract water from subsurface material, excavating it, drilling it, or sending heat down into the subsurface and having the volatiles rise up out of the regolith and get collected in a dome. Those are several of the different techniques. We're looking at different oxygen extraction techniques. As I mentioned, there's a carbothermal where methane is used to bring carbon into a molten material. We have molten regolith electrolysis, where we make the regolith molten, stick in electrodes, and try to separate the oxygen and the metals that way. Ionic liquids are a type of acid and bases, and then plasma reduction, as I mentioned. And then once we get the water, we have several techniques that we're considering on how we would break that water up into oxygen and hydrogen. You may have heard of proton exchange membrane types of water electrolyzers, solid oxide electrolyzers, and even alkaline electrolyzers. And since we don't expect the water to be perfectly clean when we get it, we have to come up with capture and cleaning techniques to make sure that our electrolyzers and our crew can safely consume that water. And I think I've run out of time about now, so I think I'll bring it to a close. Thank you very much.
Thank you very much, Mr. Sanders. That's very comprehensive introduction there for the RSRU at I guess Johnson and NASA in general.
That is
So yeah,
correct.
yeah. So I found even though I'm not civil engineering background, I found a couple areas that really interesting to me. We have done a little bit we have some student project on developing the solar array for the lunar South Pole,
Hmm.
and we had worked on some geothermal kind of a type of system.
For
So yeah,
energy.
for energy, for extracting, possibly extracting from ice become water from underground. So those type of things. But I will not take too much time, sharing that right now. But I want open to some my colleagues if any immediate questions to Mr. Sanders.
Dr. Zhu, I have a quick question. This is Dr. Azam from Civil Engineering. Great presentation. One quick question. Apart from Mars, are you guys thinking of colonization of Moon, or that's not part of the plan? Yeah.
Well, for NASA itself, I think our objectives are, a combination of sustained human exploration and then going on to Mars. I could see initially working towards something like a Antarctica type of base, a research base where you might be able, from a NASA perspective. However, as I pointed out, NASA is trying to bring in commercial industry and such. So I could see in parallel or even an advancement of some of the things NASA does, that if we can introduce spacecraft that can go back and forth, you might start seeing things that are happening now or in Earth orbit, where companies might build habitats and companies might do research on their own. So I do see, if we can continue this program, we'll take our experience that we're starting to see in low Earth orbit, where, after the International Space Station, we may have private habitats and private industry there, that going towards the moon as well. So, colonization is in the back of our minds. It's not one of those, primary drivers that says, okay, we now have to design for, a life support system for 1,000 people. It's there. We're considering it. And interestingly enough, I think the spin-offs that we're considering for, again, let's say life support, how we clean up water for, for extracting water from the permanently shadowed craters, how we reduce CO2 on Mars for making oxygen and fuels. Those are things that we might be able to spin off here as well. That helps us. So I think those kind of things are where we're headed to. I would hesitate to say, yes, NASA is going to colonize the moon, but it's in the back of our minds.
Thank you. Thank you.
Thank you. Any other immediate questions for Mr. Sanders?
I have one question, Mr. Sanders. So actually, I'm Lei Wang. I'm assistant professor of civil engineering. And one question I have is because currently at UDC we have a NASA Center for the Advanced Manufacturing for Space Technology. So part of research I'm doing is currently I'm evaluating to develop the the drilling tools through the 3D printing to kind of doing the calibration of the lunar surface regolith. But one thing I'm also thinking, another one is in the future, possibly we can do is, possibly using these 3D printing tools to kind of from the regolith to build the, like, for example, building blocks, concrete, these things. So I'm not quite sure, like, from your perspective, how the advanced manufacturing or 3D printing, these kind of things will play in our RSRU missions.
Yeah, I see it very strongly. So I kind of separate manufacturing from construction. Okay, even though they're 3D printing, in some cases, the scale that you're talking about, the fidelity, the accuracy can be a little bit different. So let's take manufacturing. You mentioned about using 3D printing for, say, drilling instruments. The lunar regolith is extremely harsh and abrasive. So our digging tools that we have, if we're going to be digging hundreds of metric tons of regolith over a year, you know, you're going to have wear and tear. So we either bring replacement parts from Earth or we 3D print those, you know, on the moon and work that way. So we're already looking at, okay, how can I 3D print, you know, parts with lunar regolith? Do I have to pull out, you know, metal alloys, whatever the case may be? At the same time, construction, so civil engineering, one of the big things that we're considering right now is landing pads. So every time you land anywhere, it basically the rocket engines, you know, shoot the regolith off at high velocities, and we saw this during one of the Apollo missions. I think Apollo 16 landed next to Surveyor 3 or something like that, and we saw some sandblasting. If you looked at the Chinese lander on Mars, they had a single engine underneath it, and there was a crater underneath the lander after it landed. So we could definitely see, if we're building up hardware and infrastructure, habitats, solar arrays that are sticking up vertically, you're going to have to protect those things, building berms, landing pads, looking at unpressurized structures for radiation protection that you could put your habitat under, for example, and eventually building pressurized structures. There are several techniques that have been considered and worked on. For example, we had the 3D Construction Centennial Challenge, where 2 companies came in the end to try to build a habitat. One used a water-based concrete. The other used a plastic binder with mixed with regolith. There is current work looking at sintering, at, you know, doing layers of sintering one on top of the other. So those are advancing, and that's, if I go back to if you look closely at that chart that I had, I'm not sure if I used the right version, but we also have civil engineering and construction demonstrations going on at the same time, such that by the end of the decade, we hope to maybe build a demonstrated landing pad, for example.
Sure, great, thank you.
Thank you. Any other questions at this point? If not, I would request my colleagues, Dr. Wang, and then maybe Dr. Chen and Dr. Azam to present. And then I just want to mention that that under this NASA-funded center, we are actually working towards the missions under the Space Technology Mission Directorate. So one of the projects we're working on is to develop the drilling tools and understand the process, maybe through how we can, 3D print those drilling tools for the ISRU missions. So my colleagues, Dr. Wang and Dr. Chen, will share more about that in their presentation. So with that, I would pass it on to Dr. Wang. And if you have any slides, please feel free to share your screen.
Sure. Thank you, Dr. Zhu, for the introduction. Let me share the slides. Yeah. Can you see the slides now? Sure. Thank you.
Yes.
Sure. Great. Thank you, Dr. Zhu, for the introduction, and thank you, Ms. Sanders, for the very comprehensive and insightful introduction of the ISRU. So today I'm mainly giving some, overview of geotechnical research we conduct at UDC. I'm Lei Wang. I'm Assistant Professor of Geotechnical Engineering in the Civil Engineering Department. And so this is my research areas at UDC. One of the research areas that is very relevant to NASA. I think, am I sharing the screen? Let me see.
Yes.
But I did not see my slides. Let me see. Sorry. Yeah, I think, can you see it now?
Yes.
Yes.
Okay. Sorry. Yeah. So yeah, this is my research areas at UDC, including the discrete element modeling. This one is very relevant to the NASA because we are using this modeling tools to doing the evaluation, the interaction between our drilling tools and the lunar reckless. Another part of my research is doing the geotechnical reliability and optimization, the space breast activations, and also we do other modeling tools using the finite element and then finite difference modeling, and geotech earthquake engineering, and finally is model testing. So this is a summary of the facilities we have at UDC. We have a geotechnical engineering laboratory, so basically we can do all the basic testing of the geotechnical materials, soils, and aggregate. And another one, we have a concrete laboratory, so we can, for example, to evaluate the properties of the fresh-made and also, hardened concrete. And we have the material testing and structural laboratory, as well as the modeling and simulation lab. So in the modeling and simulation lab, we have both like the discrete element modeling tools, as well as finite element tools such as Plexus and COMSOL, and also finite difference tools like the FLAG. These kind of softwares for our modeling purpose. This is the current student I have been working on through this NASA Center funded research, including Jesus Brada. Actually, he's also doing interns at NASA headquarters, and he's finishing his master thesis at UDC. And Omar, and also I have recruited a few undergraduate students. They are doing like literature reviews of the different existing drilling and sampling methods used by NASA, as well as developing the designs for the bio-inspired drilling method. So this is a kind of objective of the research we are doing. So one thing is currently is because just Ms. Sanders said, in the future we want to construct the facilities to build a permanent base in the Moon and Mars, as well as the trafficability and landing process. So one critical thing is we need to understand the physical as well as the mechanical properties of lunar reckless. So this research is pretty well aligned with SRU as well as Artemis mission of the NASA. The major objective we want to do is to investigate the fundamentals between like the geo and the lunar reckless interaction, so like we can develop energy efficient geotechnical tools for drilling, as well as in situ calculation of physical and mechanical properties of our lunar reckless. So this is kind of the flow chart, what we want to do. First, we are doing some discrete element modeling of our drilling tools interacting with our lunar reckless. And through these things, we want to build an energy efficient drilling tool. What we are currently thinking is we want to develop some bio-inspired drilling method, because we all know like a lot of these biological species, when they are digging into the ground, they are much efficient than like any most efficient tools human we can develop. So we can want to kind of learning how the mechanism of their digging and their drilling to develop the 3D printing tool and print it using this 3D printing capabilities we have at UDC. Finally, we want to do the in situ calibration. But for example, we can, when we're drilling into the ground, we can based on measuring the resistance, for example, the tip resistance and friction resistance of our drill to estimate the physical and mechanical property of the lunar reckless. So this is kind of a background of the drilling method and reckless. And for example, this in the Apollo missions, basically people are using self-penetration penetrometers to measure like the resistance of the penetrometers to evaluate the properties of the lunar surface. And currently, these are some like I think this is a lunar resource proctor drill that has been experimented in some like Arctic areas to evaluate how their efficiency during the drilling. And these are the kind of the fundamentals of the lunar regulus. And most time we are using some like lunar regulus simulant to simulate the lunar regulus when we are doing the experiment. So there are some collected samples from the Apollo missions, and also there are also different types of lunar regulus simulants. For example, the JSC is one of the very commonly used. And these lunar regulus, they are very fine particles. The majority particle size is from 0.01 millimeter to 3 millimeter, and the density is from 1.5 to 1.7 gram per cubic centimeter. And one of the challenges is there is low gravity, so it's very difficult for us to, doing the experiment in the Earth. One thing we want to do is we want to using the modeling tools to evaluate, the interactions between our lunar regulus and the drilling. So the method we use is called discrete element method. So it is a particle-based numerical method to modeling the granular materials. So the lunar regulus, basically, it is unbounded, kind of the particle size like the silt in the Earth. This method involves like particles as well as boundaries. And we are modeling the interparticle behavior through different contact models, such as the linear elastic model. And we'll use the Newton's second law, kind of, we know like the contact between the solid particles, then as their contact behavior, kind of using Newton's second law, we can know like under certain force, what will be the acceleration, the displacement. And then through the integration, we can get time integration. We can know the kinematics of the velocity at different time during our modeling process. So this is the pro and cons of our DM modeling. One thing is it can direct modeling the behavior between the solid particles in the particle levels. Another one is it will bypass the constitutive model typically we model for the solid behavior. So it is more accurate in the modeling, and also it can suitable to solving the large deformation problem. For example, when we drain into a ground, or if we are doing the excavation, they involve large deformation problem. And also it can be very helpful for us to modeling like in the low gravity environment. And but one drawback is very computationally expensive in the modeling.
Do you consider irregular shaped particles or just spherical?
We can model it either the sphere or irregular particles. So currently, what we are doing is we are modeling using the sphere particles, but we can build the clumps based on the sphere particles. Then we can model the irregularity of the particle shape in our modeling. Yes.
Okay. You also might want to think about electrostatic interactions between particles that might play into something downstream.
Sure. Great. Yeah. Yes. So yeah, currently, we are modeling, using the sphere particles. This one is one of the model we have been run. So kind of we are model half of the model. So basically, we use a particle size from 0.1 millimeter to 0.2 millimeter, and we use a size of gel of 2.5 centimeter. I think this is the same size used for the TRL6, is the lunar resource proctor gel. And we model the gravity in the moon, and we evaluate under different excavation depths, what is our ball velocity, the displacement, as well as contact force chain. So under different velocities. And also we model like a whole model. But one thing is, if we model whole model, there will be more soil particles in the modeling. So if we use a small, particle size, it will just running a lot of time. So what we are doing is we kind of enlarge the particle size. Then this is some animations, when we are drilling into the ground, lunar regolith. So what is the change of the ball velocity and as well as the contact force during our drilling. So kind of we can see when we are penetrating the ground, the contact force has been increasing. One thing what we can do is we can just based on the resistance force during our penetration, kind of to evaluate, for example, different densities or different fixed angle or strengths of the soil particles will have different contact force. Through this way, we can do the back calculation of our lunar properties, so like we can do the in situ calculation. And this one is something like we are doing like for the three-dimensional modeling. This one actually it will take more computational resources during our modeling. But one thing is the 3D modeling, it can we can modeling how the load application process. For example, as far as I know, currently NASA is using some percussive rotary drilling. So one thing is the 2D modeling is really hard for us to modeling this very complicated drilling process, but we can do it using our 3D modeling. So another one we want to in the future to do is to think about the bioinspector drilling. For example, one thing is a lot of the living species, such as ants, when they are digging into the ground, they are 100 to 1,000 times more efficient than the tunnel boring machine currently we have. Also, there are some other species such as the Atlantic razor clam, using their long, slender, razor-like shell to slide through the dense sand. So kind of they are shrink and expanding their body, so like they can even fluidize the sand to reduce the resistance, so like they can have more efficient drilling. So kind of what we want to, next step we want to do is we want to evaluate these bio-inspired burrowing mechanism and kinematics. So like based on these principles, we want to develop more energy efficient drilling tools for the RSFU purpose in the future. Another one is during the drilling process, one thing is there will be heating generated, especially, for example, if we encounter the ice-bearing regolith. So how the interaction between our drilling tool and the regolith due to the thermal effect will be something we are interested, and based on this one, how we can optimize our drilling process. And finally, we want to build these drilling tools using the metal 3D printing capabilities we have at UDC. And this one is some STEM outreach activities we have at UDC. So basically, including we have some like we have a very successful student ambassador program. So basically, the undergraduate student in different engineering majors, such as civil engineering, mechanical engineering, computer science, they will serve as student ambassadors to go to like different high schools and community colleges to engage with them different STEM activities. And also we have summer workshops for the high school kids as well as community college students, which including also the NASA relevant components. And these are some like our student ambassadors work at different schools. They have been very successful, go to different schools and to attract the student interest about STEM as well as related to the NASA. And also we have the guest lecture series at UDC. We invite the speakers from the such as federal agencies and other universities to give presentations about researches related to geotechnical concrete, to spark the student interest in this field. And these are some other research I conducted, for example, the brisk aviation. So basically, this one is we are, for example, this one is we are evaluating the when we're doing the excavation, what will be the ground responses. What we can do is we are doing a small scale experiment first. Then we evaluate the performance during our excavation process. So, possibly in the future, one thing is the NASA is also interested in the excavation process. One thing is maybe we can do some modeling for the doing this excavation for the NASA too. Sure, thank you.
Yeah, thank you very much, Dr. Wang. I'm not sure, Dr. Chen and Dr. Azam, do you want to present your research?
Yeah, I have a few slides. If I can share my screen, I can show them. Sorry, I have trouble sharing my screen right now.
Yeah, so Mr. Stan, go ahead.
Sorry, I have to quit Microsoft to it's now sharing my PowerPoint.
Dr. Zhu, I can go ahead, and then when Dr. Chen is
that's okay.
Sure.
Yeah, that works. I'll just quit and reopen.
Okay.
So yeah, Dr. Azam, please go ahead.
Sure. Give me a second. I'm just loading. Okay.
Yeah.
Can you see my slides?
Yeah.
Yes.
Yes.
Okay. Okay.
Can you see the full slide, full window?
Yes.
Zhu? Okay.
Yes.
Thank you again.
Yes.
I appreciate Dr. Zhu for inviting me and us to this event. I think it's very exciting, and I appreciate the NASA scientists here who are willing to listen to us. So my name is Hussain Azam. So my specialty area is environmental engineering. I'm the assistant professor here at the Department of Civil Engineering. Two of my students should be actually here, Jonas Lee and Stephanie Fuentes. And there are some relevant projects that could be very relevant to NASA's priority areas. I never knew before, but I think I know now. So, so hopefully we can build some projects together. So I just wanted to, as NASA folks knows it very clearly, but you guys have the critical path roadmap in the advanced life support program like ALS, and one of the areas that I feel like I can significantly contribute is the type 2 very serious your ALS, food and nutrition and environmental health areas where I can significantly contribute, like maintaining acceptable atmosphere in the habitable areas, like inability to provide and recover potable water, and also like inadequate supplies. I work in a little bit of aquaponic hydroponics area as well. Could be useful. Like I treat solid waste, and I know the solid waste is a big problem because NASA, if I know correctly, bring most of their waste back to Earth, and they are looking for malnutrition issues and also inadequate storage issues. So I feel like I can significantly contribute to those priority areas of NASA. And I was looking into your current ISS, the system that you have to supply water and oxygen. So you have the urine processor assembly, water processor assembly, and oxygen generator assembly, as well as CO2 reduction systems. And a lot of the project or research that I do fit well with this type of water recovery system or oxygen generation systems like that. And I actually proposed a project yesterday to NEAC program. Hopefully it will go through. But fundamentally, I'm a water, energy, food, climate nexus person. I mainly look into wastewater with solid waste and other type of drinking water issues. So I look into carbon removal and absorption, and we look into nutrient removal and recovery, and sludge treatment and energy recovery, and algae and energy treatment. And I use some advanced process chemistry and microbial ecology with advanced instrumentation tools to look into all my projects. And I will briefly show you or tell you how it connected with NASA in a second. So I felt like the collaboration value to NASA will be different areas of land and vegetation or oceans that I have some collaborative project. I'm not an expert in modeling, but I have some collaborator. We are working together on like remote sensing of harmful algal bloom, which could be something of interest to NASA. And I told you like some of the water, energy, food nexus issues for space exploration could be something, could be a big interest to you. Based on your presentation today, I work with a lot with different minerals as well. And then that could be also very, very relevant to your presentation today. So one of the projects I just proposed and one of my students proposed to NASA last few months is one is the synergistic roles of recoverable in situ materials to support human life of Earth. Means like because you can recover a lot of materials from your system that like the space mission that you are conducting. You can recover struvite from your waste or wastewater. We are thinking of that in the future. If you do colonization, you might need to have hydroponic aquaponic system so you can recover like chitosan or cytosan like or activated carbon or biochar that you can generate from your waste. You are talking about reusing a lot of materials from lunar or Mars, like zeolite, silica gel, palladium. Those kind of material could be recovered and can be used to air quality control, water recovery, and waste treatment for sustainable food production. So we propose some ideas. Hopefully, it will go through. And as you can see, we can recover materials from urine. We can recover materials from waste. We can recover materials from like a shrimp, or we can recover some of the existing materials or minerals you have in Mars or Moon, and we can use them for air management, water recovery, waste treatment, and food production. One of the area could be also that the solid waste that you bring back. I have an existing project that I'm doing, not for, of course, NASA, that we look into digesters and we look into solid digestion, means all the waste that we generate, food waste, grease interceptor waste, and we run through digester to recover methane and hydrogen. So energy issue also is an important aspect. So we might be able to recover some energy resources. Actually, I'm not talking here, but there is a potential for recovering different minerals like struvite and other processes from this type of systems. One more project could be very relevant, and you guys were talking about recovering different materials from lunar surface or Mars. I have a project that looks into struvite dissolution and inhibition with recovery potential. So we use chelating agents to dissolve some of the minerals that we have in wastewater systems, but we recovered them later again in a controlled manner, because it is a nuisance when it is somewhere that you don't want them, maybe in the lunar surface or Mars, and then you can use it to recover where you need them. And why you want to recover this type of materials? Because struvite is a fertilizer. You can supplement your food production system. Struvite has potential to remove a lot of water and air contaminants. I know NASA has their big list of 55 air pollutants, if I'm right, and maybe I forgot the total number, maybe 25 water pollutants. They are very concerned of to support human life of Earth, and these type of materials could be useful to use. With that, I just want to close out. If you have any question, I can answer that. But I feel like in the ALS program, I can significantly contribute to NASA. Thank you, Dr. Zhu and others.
Yeah, just quickly, my area of expertise is not life support systems, but we are, for ISRU, we are looking at both biological and physical chemical plant type aspects.
Okay.
There is a balancing act between the two in terms of, again, the size of your crew and how much volume you need and such.
Mm-hmm.
So I think the biological processes that we're looking at will start making sense when you are not as volume restricted or as your crew size starts going up. And I completely agree that there's a lot of spin-offs and spin-ins with what we're doing terrestrially. But you know, one of the issues that we still need to work with in terms of Mars, for example, is that planetary protection rules. Anytime you bring a biological reactant or whatever to Mars, you would then have to worry about how you would contain it or what impact it would have if it was released and such. So,
sure.
And the space environment is pretty harsh. The radiation and such could lead to unacceptable levels of mutation or killing off your biological agent. So some things to consider there.
Yes.
That we're also thinking about.
Sure, thank you. And you talked about the payload and how the typical mass can increase $1 billion of your costs for. So reducing the load and everything could be something we can consider some of the projects.
Yeah. But thank you.
Thank you. Thank you.
I guess, yeah, it's my turn. Sorry. Yes. So let me share my screen. Hold on. Can you see my screen?
Yes.
Let me
yes.
put it in play mode. Are you looking at the big screen? Or it's
yes, I think this is the
main screen, right?
The main screen. Yeah.
Okay, thank you. Thanks, Dr. Xu, and thanks, Mr. Sandra, for that comprehensive talk. Apologize for the technical difficulties. So this one actually follows Dr. Wang's talk on DEM. So I'm Qiuxi Chen, Associate Professor of Civil Engineering from Clemson University. So I'm collaborating with Dr. Wang on task 3 on DEM modeling of granular regulus materials. So I'm going to give you an overview of our efforts on characterization and computational modeling of granular materials. And I have a student partially supported on this starting summer 2021, and there's a new postdoc hired by Dr. Wang. He will start fall of 2021. So basically, for my presentation, so first I want to go over basically what we do in computational geomechanics lab at Clemson, and then I want to show a couple of research efforts that are relevant to this project, and briefly I'll talk about how we collaborate with UDC to support this project. So in our group, our research interests are the computational modeling of granular materials and their interaction with engineering systems. I'm listing here 3 materials that we study in our group. 2 are basically simulants, lunar and Martian simulants. And then we also look at conventional geomaterials and the biomass feedstocks. So a common feature of these materials, they are all granular and porous materials. So in terms of the resources we have, so some of the tools Dr. Wang mentioned in his presentation, so we have access, we have license to a suite of modeling software including lights, which is an open source discrete element method code. Then we have access to two commercial codes. And then through Clemson's campus license, we have a suite of Altair tool, including EDM, and also Abacus and ANSYS are finite element analysis software. In our soil mechanics lab, we have equipment for typical physical characterization and mechanical testing, including triaxial, direct shear, sieve analysis, permeability. So all these standard tests for geomaterials and regular simulants. And Clemson also has Palmetto, which is a high-performance computing cluster that is free for all faculty and students at Clemson. Here I'm listing some relevant publications from our group recently. The first two focus on either the characterization or the computational modeling of Martian regular simulant. And the third one is our recent efforts on biosegmentation of Martian regular simulants. And last two are related to discrete element modeling of biomass feedstock particles. In terms of relevant research highlights, so I want to briefly focus on two. The first one is discrete element modeling of lunar and Martian regular simulants. And the second is image-based microstructure analysis and modeling. And for the first one, this is basically a summary slide Dr. Wang showed in his presentation, covers the basics of DM. So I'm going to skip this slide, but this is basically the method we use to model the mechanical behavior of regulars and also their interaction with drilling or sampling tools. So the first effort regarding the DM modeling of regulars. So this is one of the projects we completed recently, where our objective is to model and investigate the effects of particle shape on the shearing resistance of a particular type of simulant, which is a JSC1 Martian simulant. For this project, for this effort, we obtained the basic regulus particle size and particle shapes from X-ray computed tomography imaging analysis, and then we construct discrete element models. And this model is built in PFC2D, so it's a two-dimensional model where we use overlapping discrete element cluster or ODEC to approximate various shapes characterized from X-ray CT images. And we also fit the particle size distribution using the experimental data we have for this particular type of simulant. And this is just a snapshot of some of the results we obtained from these modeling efforts. In terms of the shape effect on shearing resistance, so by comparing the shearing resistance from irregular shaped particle models to disc-shaped particle and disc with rolling resistance models, we found that the shape irregularity contributes to about 40% of the shearing resistance. And then also shape irregularity prohibits particle rolling and promotes particle interlocking. So basically it adds the resistance, so shape irregularity adds resistance to the granular assembly. The other recent efforts, this is directly supporting the modeling effort Dr. Wang just mentioned. At Clemson, for this project, we are developing 3D DM models. And the first one we are looking at is a triaxial testing model for realistic regulus behavior. And the purpose of developing such 3D model with realistic particle shapes and distribution is to support the regulus tool interaction simulations later we're going to do in this project. And for this effort, we are using an open source called Lights, and we are implementing realistic particle shapes through a clamp, particle clamp, which is basically very similar to that ODEC approach. And for triaxial tests, we're looking at using bounded sphere model to basically capture the flexible membrane wall that's surrounding the particles. And so shown on this slide, the left one is a demonstration of the triaxial testing model in development. And on the right-hand side is basically a simple verification of particle clamps for capturing irregular particle shapes. The other research effort that's relevant is basically image-based microstructure analysis and modeling. So shown on slide is an example of the work we are doing in this area. So we have access to X-ray CT scanner at Idaho National Lab. And shown here is an example of the scanned particle. This is for a biomass feedstock, but we can use the same approach, or we have used the same approach for regulus material as well. And once you obtain this scanned particle from X-ray CT images, then you can reconstruct its 3D microstructure and perform microstructure analysis or build a discrete element model to predict its mechanical behavior. These next two slides are some technical details of the methodology we developed. One is a conventional threshold method to process X-ray CT images and construct a 3D microstructure. And the other one is a machine learning enabled framework where we used a particular technique called trainable Wagner segmentation to process X-ray CT images and segregate lunar regulus particles, or this is Martian regulus particles in contact, then extract realistic particle shapes, perform analysis, and construct numerical model. So this slide summarizes two applications. The left one is image-based microporosity analysis, where using X-ray CT images, we can analyze the microstructure features of the material. In this case, it's loop lolipines. And on the right-hand side is image-based particle reconstruction and modeling applied to JSC 1A Martian simulants, where we characterize particle shapes and also build realistic 3D models to predict its mechanical behavior. So this is something that we can use when we simulate particle-to interaction. And finally, I want to briefly mention in terms of how we collaborate. So at Clemson, as I mentioned, our main role is to support task 3. That's the task Dr. Wang is leading. And we focus on develop 3D DEM models and its implementation in open source code LIGHTS for modeling the mechanical behavior of lunar and Martian regulus, and also for modeling their interaction with drilling and sampling tools. And also I co-advise students at UDC on DEM modeling for their model in PFC 2D and 3D. In terms of the students, as I mentioned, we have one student partially supported at Clemson starting this summer, and then we have a new postdoc starting September at UDC that I will co-advise with Dr. Xu and Dr. Wang. I think that concludes my talk. Thank you for your attention.
Thank you.
Thank you, Dr. Chen, for your presentation. All right. Yeah, do we have any faculty need to present or?
I think this is all the UDC side presentation. Yeah.
Okay. So now I guess we can open the question floor for all to ask, whether from the NASA presenter or our UDC presenter. So if you have any questions, please feel free to ask.
I just put a little note on the chat. I know whenever we deal with simulants, you know, how you make the simulants and what you're using the simulants for is a big question. And so we actually have set up a project. I can send you the point of contact that can provide advice. Anytime you deal with the moon and you're thinking about looking at physical testing or processes, you have to be very careful. For example, we started using JSC1 lunar simulants during, you know, the Constellation program in 2005 to 2011, and we found that it had too much flowability because it's produced through use of a ball mill to get the size fractions. Whereas when we started to use other simulants like the Lunar Highland type or OB1 from Canada that had a different method and different minerals, the behavior was much closer. We have a video, for example, where Kennedy Space Center was working on a mineral beneficiation technology and had requested actual lunar regolith from the sample curation facility. And before you're allowed to accept that, you have to show all your processes ahead of time with simulants.
Right.
And they had a video of them pouring the JSC1 through a 1/4-inch glass funnel, and it went straight through. When they actually got the Apollo 16 material and poured it into the glass funnel, it bridged, and they actually had to tap it repeatedly to get small amounts of the regolith to fall through. So we kind of figured it was a combination of potentially electrostatics because it was a dry nitrogen environment, as well as the very irregular shape of the regolith. So I saw the picture of the hopper and the material flowing, and the Kennedy Space Center has done some very interesting work on, hopper geometries and looking at different simulants. They flew, Vomit Comet flights. So I would definitely look at, look up, some of that research as an example of where you might, consider certain aspects.
Okay. Thank you, Mr. Sanders, for that comment. Yeah, we would really appreciate if you can help us put in contact with NASA scientists working in this area. Yeah, I think in our DM simulation, we did find that particle shapes have a great impact on the mechanical behavior, including its compressibility and the flowability. I think that's something, it's one of the focuses we have in our model, is to capture the realistic behavior of the real lunar regoliths.
Yeah, it's Mars, as I put in the chat, Mars material is much easier to represent because it has gone through weathering processes at least reasonably similar to Earth. A long time ago there was water modification. Now there's a lot of wind modification and thermal cycling. Whereas lunar regolith is much more difficult because it didn't go through the same kind of weathering. It was created through much more impact-like shock situations. And then what even makes it more difficult is, a significant fraction of the lunar regolith is something called agglutinates, and I didn't even cover that, where whenever you have an impact, where the impact occurs, there's enough heat energy from the impact that it causes some of the granular material to sinter and melt. And so you get these very interesting 3-dimensional structures, but they're kind of like sugar cube strength. And so they will definitely crush and change shape if you start applying a force. So as you had in those models, it's not just the irregular grains, but you will have some, agglutinate structures which will actually, under certain force loads, crush and change and flow differently. And I don't know of anybody at the moment that has really done DEM on that type of situation. And as you pointed out, it's all very computationally intensive.
Right. Yeah. I think that's an aspect where we could benefit greatly by talking to scientists like you and others working in the ES area, so we know which aspect should we follow in our efforts to better align with NASA's research there.
And getting some lessons learned, because I know I've seen some DEM work on blade soil interactions and wheel soil interactions in terms of how the different treads interact with the surface and how it flows, and so there's been some interesting work that has been done in the past that hopefully they have documented not just the results, but what worked, what didn't, and and in particular what assumptions did they make.
Right, that's right.
Also, Ms. Sanders, I have one question, because we are doing some BDM modeling of the drilling, and another part is we want to also interested to do some model testing. Actually, I have one slide at the end, but for some reason it could not show at the end. So may I know where there is some testing data available, so we can know for example, NASA already did some interaction between the drill and the soil in a low gravity environment. Kind of we can do some comparison of the result with our modeling result.
Yeah, I mean, you probably need to make some kind of an agreement with Honeybee Robotics and Chris Zachney. The bulk of the testing data that we have at the moment is based on the Lunar Prospector Viper drill that that you mentioned. It's officially called the Trident drill, I believe. And so we've been working with them. We've done testing of their auger into ice cemented regolith under vacuum conditions. They've done testing in Antarctica. So really, I think looking at papers by Chris Zachney,
Would you mind type it in the chat?
Oh yeah,
Chris, thank you.
I know we ran out of time, Dr. Zhu. Can I just have a quick request to Mr. Sanders?
Yeah,
go ahead.
Yeah, so if you can connect me with people who are working with like a solid waste, and also the water recovery, who is leading that, or air pollution control or air.
Yeah, that's an area that's outside my expertise.
Right.
Whoever your main contact is at JSC, I would recommend that he follow up on that one.
Okay.
I do work with the life support folks, and we are looking at solid waste processing, but from our perspective, we're looking at it from when the life support folks are done. And so, for example, I'm aware of two different aspects. One is, the drying of human waste.
Yes.
And then they basically, bag it and throw that away in the spacecrafts that burn up. The other is the kind of plastic waste and the container waste and things like that, the packaging waste. They are currently looking at just what's called the heat melt compaction unit, where they take that and they compact it and heat it and turn it into like hockey pucks, dense hockey pucks.
Sure.
The Kennedy Space Center has been working on steam reforming of waste of those, as well as oxidation and pyrolysis of the waste.
Sure.
Again, that's more the plastic waste type of stuff. The biological waste, there are issues with handling that potentially, and so that's why the ISRU community is just mostly thinking about packaging waste. But here again, that's the air and water and human waste aspects are things outside my area, and I if I tried to find somebody, I probably would find the wrong person.
Yes, thank you. Appreciate it.
Thank you. So Dr. Azam, so we have actually requested someone from their area to come to today's meeting, but he need a little bit of advance time and could not make it. But we will put you in contact with them, and hopefully we can have some future sessions that we can have you to network and discuss your research with them. So
Thank you.
That's on our agenda. So yeah. And So, Mr. Sanders, I just want to kind of share with you also that we are also very interested in maybe having some UDC students to do some collaborative projects. So we have a couple of students, starting their master, PhD programs here. That if possible, we would like to have some mentorship from NASA Johnson on those areas. I know Dr. Azam had a student apply for a fellowship, a NASA fellowship for one of his students as well. So yeah, so we want to support our students that they can get some direct mentorship experience from NASA, and also we have some students doing internship at NASA or had an internship before, so we're still looking forward to have more our students that can participate in the NASA internship, in particular the areas maybe RSRU or some relevant areas as well.
So there's different. I'm sure you're aware of the different methods. You can have a relationship directly with the Johnson Space Center or a different center where, mentors basically are kind of, I'll say, for free, but there's no real exchange of funds from NASA going to you guys. And obviously the mentorship can't be too excessive, because then there would be charge code issues. So those things we can set up, I'm sure, at some point. There's also the NSTRF, or I think they've changed the name to NSGROW, which is the NASA Student Research Grant program, where every year, I don't think it works for undergraduate. I think it's either masters or doctorates, where basically you can put in for a student could put in for a research on different particular topics. At the same time, we have the same type of thing for faculty. Early career ECFs, early career faculty folks, can set up research activities, and those are much better in terms of NASA actually providing funding for those things versus just ad hoc mentorships. Sure. So those are different things. We also, something to keep in mind, NASA just introduced a new program called Luster, and they had their first activity solicitation this year with selections. Luster stands for lunar. I can't remember. But it's basically university based, and it's university research for the moon. It's 2 to 3 year programs. And again, all of this is run out of the Space Technology Mission Directorate. So if you look under that heading, then you might be able to find these things. So I think, part of it is to make sure that, we understand what type of research you want to do, and then we could try to match what the right subject matter expert would be, for that kind of thing.
Yes, yeah, that's right.
And can we send up maybe Mr. Sanders follow-up emails? So Dr. Wang, for our task, we're focusing on the regular side and maybe regular drill interaction for ISRU. Maybe we can send you a follow-up email. So
yeah.
Mm-hmm.
Yes.
And as you pointed out, we're looking at using, 2 types of drills at the moment: auger drills for sample collection, as well as potentially material collection for extremely hard regolith. If it's consolidated icy regolith, it could be as hard as concrete. So how you break through that, an auger drill might be something of interest. Rotary percussive, as mentioned. We are looking at cone penetrometers, but only for near surface type of situation for the geotechnical. Then we're also, if you look up, do a Google search on PVEX. That's a honeybee coring drill, and basically it's planetary volatile extractor, I think. And it's a different type of coring drill where you core into the lunar icy regolith and you try to heat the material in situ. So now instead of, you know, a rotary percussive auger where you have your, you know, your flutes and everything, you now have more of a circular drilling surface, and that changes your dynamics, obviously. How you deal with the auger flutes on the outside to move material also adds complexity to your DEM. And so I know Honeybee has done some papers, and Chris Zachney has done some papers on, you know, changing the auger flute diameters and angles depending on the regolith properties and such. So it's there's a lot of past work in that area that's been documented. I think, you know, Chris has partnered in several books on extraterrestrial drilling. If you've not seen those, definitely I suggest you get a copy.
Sure.
Okay, that's very helpful. Yeah, we have actually done extensive literature search on the current tools developed for lunar and Martian missions. I think before this meeting, I think one of our biggest question is which one should we focus moving forward? Because there are so many efforts out there by either NASA, by Honeybee, or by European agencies. So I think for us, we need to focus on the one that's most relevant to NASA's near future missions. I think the information you provided is very, very helpful to us.
Yeah.
Thank you.
No problem.
Thank you.
Great. Thank you very much for the suggestion and feedback. Is there any questions for? I know we have a couple of students in the audience. We may not have time for them to present today. We don't want it's already over the scheduled time. But if there's questions from the student, you know, please feel free to either type in the chat box, or you know, you can just unmute yourself and ask. We also saw a couple of faculty members joining as well. So if any questions, please feel free to ask. So while we are waiting for the maybe some questions from the students, I just want to kind of, this is from one previous comment from Mr. Sanders, that you mentioned that the lunar resources prospector drill is being used on the Viper. I know Viper is supposed to be launched next year, I believe. You know, we are working with another group at Johnson. You know, we have a couple of interns this summer as well, helping with processing some of the experimental data they collected from the testing of the Viper. And also one of the areas we had a meeting before that was suggested was to look at like the thermal effect of the drills, and you know, how that can be kind of integrated into the design and optimization of the drill. So I don't know if you have any comments or suggestions on that.
Well, obviously, yes. So there is the Trident drill has a temperature probe at the front of it. and depending on the weight on bit and the speed of rotation and such, you could introduce frictional heat, where you could be concerned with starting to vaporize the water, ice, and other volatiles. So there is some work going on to basically understand how that could be, could influence things. One of the issues that we have at the moment is we really don't know what the material is like in the permanently shadowed crater. So a lot of the testing that we've done to date has been with what I'll call the ice cemented approach, where you take lunar regolith simulant, you add a certain amount of water to it from a weight percentage perspective, you then freeze it in different layers, and then you add those layers into a tube for drilling tests, and you put that into a vacuum chamber. And what you get typically is, once you get to around 4 or 5% water, you start getting a very hard, cemented type of consolidated material. The Colorado School of Mines has taken a different approach and started to look at what I'll call the shaved ice, where under a freezer condition, you shave ice into ice granules, and you mix that physically with granular regolith. So now you have a more granular icy regolith mixture, and depending on and I need to start using their chart, but they recently presented a chart at the PTMSS conference where they showed water ice could exist in nine different forms in the permanently shadowed crater, how it cements the different particles together and such. And so I think those are the two extremes. So testing and modeling both of those, are areas that we're interested in now, but how do we take into consideration some of those other ones that we haven't been able to figure out? That's high on our list of activities. Prime 1 will fly next year. That's just the drill and a mass spectrometer. Viper will fly in 2 years. So December of 23, whereas Prime 1 will hopefully fly in December of 22.
Okay.
I have a quick question on one of the previous comments Mr. Sander made. So on the lunar simulants part, so you mentioned that the JSC 1A is probably too much flow. So it's the Highland simulants, the one mainly used for some of the tool development, or are there any other primary simulants?
Yeah, I'm not sure what there's several companies now that make simulants. We made a whole bunch of lunar Highland type simulant back during Constellation, and I don't know there's probably not a lot of that around. Like I said, I'll send you a point of contact at NASA on simulants that you can discuss what might be the best simulant to use for lunar physical testing. I kind of like the OB1 from Canada. It's made using more of a compaction type of milling versus a ball mill, so it's got much more shagged. They also use a slag component from a local nickel processing, so even though it's not minerally correct, it's got an extremely hard, glassy, abrasive component to it. I think there's a company that sells green spar, anorthosite on the market. And again, the Highlands is, and then there's two companies, the University of Central Florida has Exolith Labs, I think, and then there's Outworld Research or something like that does simulants. So like I said, I'll send you the NASA contact for simulants, and I recommend that you open up a dialogue in terms of what you're trying to do, and when you get to testing, what would be the right one.
Okay, yeah, that would be very helpful. Yeah, we recently actually purchased some LHS Highland simulant and the Mare simulants from University of Central Florida, their lab. So we got a couple of boxes of that simulants, but we don't have OB1 or any other ones they are currently using.
Yeah. Okay.
Thank you. Thank you.
Yes, thank you very much. I know we are over time now, so I don't have any other questions. If not, I would like to thank Mr. Sanders from Johnson for very detailed presentation and also all the useful discussion and we had today. And also I want to thank the Scott and Brandon from Johnson for coordinating this event, and also my colleagues and students who have participated in today's discussion. Thank you all for joining this event today. So with that,
thank you, Dr. Xu, for organizing this. Thank you for inviting us.
You're welcome. So I will be sharing the slides after today's session, and if you have questions, please feel free to reach out to us. So and I look forward to more discussions with the ISRU group and UDC in the future. Thank you.
Thank you.
Thank you, Ms. Sanders. Thank you, Dr. Xu.
Thank you, Mr. Sanders.
Thank you, Mr. Sanders.
Thank you. Have a good day.
You too.
Bye.
Bye-bye.
Bye.